Hi, I'm Junwei Zheng, a PhD student from Karlsruhe Institute of Technology. I'm presenting MateRobot, Material Recognition in Wearable Robotics for people with visual impairments. In 2020, there are 43 million people with visual impairments around the world, and this number is expected to be 61 million in 2050. There are lots of challenges in their daily life, for example, navigation and mobility, access to information, social interactions, employments, educations, and so on. Among all challenges, material recognition is one of the most challenging but important ones, since visually impaired people know about the material of an object mainly through touching. However, not all stuff and objects are touchable, for example, electricity, fire, and so on. Knowing stuff and objects only through touching is potentially dangerous for blind people. Peter is one of them. He always complains about falling on the snowy sidewalk in the winter, and also he gets wet when passing by the puddle. So how can we solve Peter's problem? Our answer is knowing the object and its materials beforehand without touching to avoid potential danger. Here, I want to firstly introduce the hardware of our MateRobot. It consists of a pair of smart glasses, a power bank, and a portable GPU for the calculation. Inside the smart glasses, there is a color camera for the RGB information and two infrared cameras for the depth information. We also integrate the bone-conducted earphone to the smart glasses, offering the voice notification to the blind users. Besides the hardware, we propose an efficient MateVid model to enable the deployment of resource-intensive vid-based model on resource-constrained mobile platform by using a learnable importance sampling strategy. A multi-gate mixture of ASPER is designed to simultaneously perform object and material semantic segmentation in one unified model. Now let's have a look at the learnable importance sampling strategy. An image is first divided into different patches and fed into the flattened and projection layer to get the image tokens. The tokens are then forwarded to the normal transformer block. The learnable importance sampling strategy happens in the multi-head self-attention layer. Since we apply the softmax activation function along the row axis, the sum of all values in each row should be equal to 1. However, the sum of all values in each column is not equal to 1, which indicates the importance of different image patches. So we sum up all values in each column, average them among different heads, and then select the top k values of this selection vector. We can use the index of these k values to select the most important k image tokens in the transformer block. Now the key question is this the learnable importance sampling strategy differentiable? The answer is yes, because all operations within the blue circle don't have any learnable parameters. The learnable parameters exist in the process of attention map calculation. Another contribution of our work is the multi-gate mixture of ASPER. Now let's have a look at this block. We have two gates in our case. One is for object recognition, the other one is for material recognition. All image tokens are fed into the first gate to get the selection vector. We know that the first two values of the selection vector are the biggest values, so we select ASPER 1 and 2. Then all image tokens are fed into ASPER 1 and 2, multiplied by the value from previous selection vector, add them together so that we can get the final image tokens for object recognition. In order to get the final semantic segmentation prediction of the object recognition, we just need to use a decoder head to decode the image tokens. As for the material recognition, we do the same operation as the object recognition. Our MateRobot achieves sorted results on DMS dataset for material recognition. Our MateVid has the smallest G-flops, while the best results on pixel accuracy and MIOU. Since we use multi-gate mixture of ASPER, our MateVid has more parameters than other counterparts. However, G-flops is more important than the M parameters for the fast inference, since G-flops indicates the computational complexity, while M parameters indicates the space and memory occupation. As for the performance of multitask learning for both object and material recognition, our MateVid also achieves the smallest G-flops, while the best performance on MIOU. This is the visualization of both object segmentation and material segmentation. The first column is the input image, the second one is the object segmentation, and the third one is the material segmentation. We can see that our MateRobot can correctly predict the object and its corresponding material. For example, the combination of road and asphalt can be an asphaltic road. We also conduct a user study. Besides the NASA task load index and system usability scale, we conduct a 2-round experiment for a better evaluation of our system. The first round is to recognize object and its materials with touching, while the second round is using our MateRobot without touching. From the table, we know that our MateRobot achieved competitive results compared to the ones with touching. As for the response time, our MateRobot is even faster than the one with touching. Here are some comments from the questionnaire. Around 67% participants were amazed by the fast response of the wearable robot. All participants found the wearable robot helpful and useful for visually impaired people. Voice feedback frequency of the glasses should be adjustable. Apart from the object and material recognition, our wearable robot can also achieve real-time depth estimation, orientation, and so on. This is a demo for these additional functionalities. To summarize, we built a wearable robotics system, MateRobot, for object and material recognition. We propose an efficient main-fit model to enable the deployment on resource-constrained mobile platforms by using a learnable importance sampling strategy. A multi-gate mixture of aspect method is designed to simultaneously perform object and material semantic segmentation in one unified model. A task-oriented user study provides variable insights for designing variable material recognition system for visually impaired people. Thank you for listening.